Good day everyone. Today we are going to discuss about basic physics of ultrasound. Before we are going to deal with basic physics of ultrasound, we need to discuss about sound. The sound is nothing but mechanical waves, mechanical longitudinal waves which travels in a straight line, and it requires a medium. It doesn't travels in vacuum. Then we have different medias: air media, water media, and solid media. Here we can see in air media the molecules are placed with some distance, whereas in water molecules they are closely packed. Relatively, the media will have more closely packed molecules. This is nothing but alternative compression and rarefaction of the molecules. This is because of compression and alternative compression rarefaction of molecules. Here, because of the molecules are placed somewhat with some distance, the waves which are going to travel in air media has a different velocity as compared with water. The approximate velocity is around 300 for air media, whereas 1500 for water media, and approximately 5000 meters per second in solid media, because of the closely packed molecules, because it depends upon the density of the media. Okay, now in human living biological tissues, the average velocity of a sound is approximately 1540 meters per second. It differs, but we are taking it as constant. It's approximately 1540 meters per second. Then whenever we are dealing with waveform, we have to discuss about four components. The first component is wavelength. Second component is frequency. Third component is amplitude. Fourth component is velocity. What do you mean by wavelength? Here we can see a complete wave is, we can see this is the complete wave, single wave. It's a sinusoidal wave. The distance between successive crest or trough is what we called as wavelength. Frequency is nothing but number of vibrations per second. Let us consider this is an frequency. The time taken is 1 second. Here the frequency is, the number of vibrations is 2 per second, whereas here you can see it's approximately 0.5 second. Here the number of vibrations is 3 per 0.5 seconds. So 1 second will be approximately 6 cycles. So here it has higher frequency. Here we can see it's a lower frequency. So the higher and lower frequency, here the wavelength, whenever there is an higher frequency, the wavelength is small. Here we can see whenever there is a lower frequency, the wavelength is larger. Therefore, wavelength and frequency are inversely related. So wavelength is inversely proportional to frequency. Then we have another component, the amplitude. You can see height of the wave. That's what we called as amplitude. The amplitude is very important in ultrasound imaging. Whereas velocity, we know biological tissue we have constant 1540 meters per second. These are the four components we need to know about the sound wave. Then, what do you mean by ultrasound? Human has a capability of hearing approximately 20 kilohertz to 20,000 kilohertz. It's a normal hearing capability between 20 hertz to 20 kilohertz. Therefore, the sound which is less than 20 is what we call as infrasound. Whereas sound which is greater than 20 kilohertz, it's what we call as ultrasound. Then the sound which is between 1 megahertz to 20 megahertz is used in our diagnostic ultrasound, diagnostic medical ultrasound. So the properties which I have discussed for sound is all applicable to ultrasound. Then in ultrasound day-to-day practice, we have to know about the three basic principles of ultrasound. First, we have to produce the ultrasound waves. It is produced by a principle what we call as piezoelectric effect. Piezoelectric effect is nothing but whenever we are sending an electrical signal to a substance, when it vibrates, it will produce an wave, sound wave. Electrical energy is converted into sound energy. Whereas whenever a sound wave hits the substance, it produces an electrical energy. It's an vice versa. So it's an piezoelectric effect and reverse piezoelectric effect. The substance which is producing this effect is what we call as piezoelectric crystals. Piezoelectric crystals. The examples are quartz and lead zirconate. In our ultrasound machine, we usually use lead zirconate crystals. The size of the lead zirconate crystal decides the frequency of the ultrasound wave. Larger the size of the crystal, larger the wavelength of larger the frequency of the sound it's produced. The next principle what we are going to discuss is pulse echo principle. This is the working principle of ultrasound. Working principle. Why it's called working principle? Let us consider in World War II, the submarines use this pulse echo principle to calculate the depth at which it's traveling in the water, deep oceans. Okay, how they use this principle is, this is the undersurface of the ship. They have a system, radar system, which transmits an sound wave and it hits back the surface of the soil and it reflects an echo. So we are giving a pulse and it's reflected as echo. This is what we call as pulse echo principle. What is its implication? We have a formula, velocity is equal to displacement by time. In biological tissues, we know that in biological tissues, let us consider this is a liver. We are transmitting a sound wave inside the liver. We know that velocity of biological tissues is approximately 1540 meters per second. It's a constant. So we know the velocity and we are sending a pulse. It's reflecting back as echo. So we know the time at which it reaches the transducer. Okay, we know that time t. Then we are calculating the depth at which this echo is reflected back. We are calculating the depth at which the echo is reflected back. This echo, we are going to take the two components of this echo. One is the strength of the echo or amplitude the value amplitude of the echo, and second component is depth from which it has been reflected back. The depth from which it has been reflected back. This is the second principle is pulse echo principle. Then we have another principle, what we called as acoustic impedance. What do you mean by acoustic impedance? Previously, I have mentioned that we have air media, water media, and solid media. I said that in air media, the sound travels in a velocity of approximately 300, whereas water 1500 and solid 5000. So, whenever sound traveling from air to water, there is a strong difference between the density of this both medias. There is a strong difference between the air and water. The density difference makes the acoustic impedance. This is a strong reflector. This forms the concept of acoustic impedance. In human, that's biological tissue, we have soft tissue component and bone component and water component, that's blood component. Whenever sound wave travels through a soft tissue and hits the bone, then there is a difference in acoustic impedance between the soft tissue and bone. Then when it's the blood, there the velocity it's differ. This forms the basis of the acoustic impedance, and the waves which is reflected back at different amplitude of echoes. That's the importance of acoustic impedance. This concept is useful in application of gel. Whenever we are applying the gel, it matches the acoustic impedance of the transducer and the skin of the patient. If we are not applying the gel in between the transducer and skin, in between skin and transducer, air will be present. This air has different acoustic impedance, so that the waves which are produced from the transducer will not reach the skin. It's completely reflected back. So we are applying a gel which matches the acoustic impedance of the transducer and the skin. So all waves, sound waves which are produced in the transducer will travel into the human body. This is the significance of the acoustic impedance. Next, we are going to deal with modes of ultrasound. We know that we have A mode, M mode, B mode. Okay. First, I have mentioned that we are taking an example of 3 different reflectors at 3 different depths. First reflector, second reflector, third reflector, fourth reflector at 3 different depths. We have depth. Okay. Let us consider we are giving a pulse, same pulse of 5 megahertz to all these reflectors 1, 2, 3. The first reflector, it's in a depth of approximately 10 centimeters, whereas second reflector it's approximately 5 centimeters, third reflector approximately 2 centimeters, and fourth reflector is approximately 1 centimeter. This is an example. Okay, now what we are going to do is we are giving an 5 megahertz of ultrasound to these 4 reflectors. What will happen? Here in the first reflector, which is approximately at the depth of 10 centimeters, it reflects an echo. Okay, now we are plotting an graph. The amplitude of this echo which is reflected from a first reflector will be approximately, let us consider it's an 5. So we are plotting 5 strength, amplitude. Okay, at a distance of 10 centimeter. Then second pulse which is reflecting from 5 centimeters, the amplitude which we gain, it's approximately 10. It's approximately 10. Whereas in third reflector, as it's approximately 2 centimeters, it has 15. Whereas the fourth reflector, it will be approximately 20. So the more it travels deep, the amplitude which we get is lesser. Whereas more it travel, we are calculating the distance from which where it's reflected by a pulse echo principle, so that we can plot a graph from where it's get reflected. This is what we called as A mode or amplitude mode. We are just documenting the amplitude of the each echo which is reflected from each reflector at an approximate depth. This is what we called as amplitude mode. The same example we are going to use in another mode. We know 4 reflectors, strong reflectors at a distance of 10 centimeter, 5 centimeter, 3 centimeter, 2 centimeter. Here we can see this is reflected from 10 centimeter. This wave, this amplitude is gained from 5th centimeter. Here it's from 3rd centimeter. So this amplitude we are making it as gray and white. Gray and white. The more the amplitude, we are keeping it as more brighter. Whereas lesser the amplitude, we are keeping it as gray. At the same time, we know the depth from where it's get reflected. So it's from 10th centimeter, we are seeing it's in more depth. Whereas it's from 3rd centimeter, it's in the superficial structure. So we are making it as gray and white scale, with gray and white scale. This is what we called as grayscale imaging. Grayscale imaging. Or this is what we called as brightness mode. We are converting the amplitude into the brightness mode or B mode. Next, what we are going to do is, we know we have converted A mode. We know that a reflecting echo is converted into an amplitude. Then in B mode, we are converting the amplitude into an brightness. Whereas M mode is nothing but, M stands for motion. Whenever an object is moving, that object can be imaged by an M mode. Here we can see the moving object is producing an different waveform. So we have completed the modes of ultrasound. Then we have another concept of frequency versus penetration. We know we have, this is high frequency, this is low frequency. Let us consider it's traveling through an object. This is also traveling through an object. Here we have low frequency. Here we have high frequency. The high frequency sound, as it travels through the medium, it loses its energy as it's going into the deeper to the structures. It loses most of its energy in the superficial structures. Therefore, it won't get travel into the deep to the structure. Indirectly, we can say higher frequency will travel only for a shorter distance, otherwise known as lesser penetration, because it is attenuated by the superficial structures. Whereas because there is a lower frequency, it will travel to a longer distance into the deeper structures. Therefore, it's less attenuated by the superficial structures. So, lower the frequency, higher the penetration. higher the penetration. So it's an inversely related. Higher the frequency, lower the penetration. So this principle is we are going to apply into our transducers. We have multiple transducers. Here we are giving an example of 4 transducers. Here we have linear transducer, microconvex, curvilinear and phased array. Linear transducer has an approximate frequency. What we are going to use frequency is approximately 6 to 13 megahertz. Whereas in phased array or curvilinear transducer, we are going to use an approximate frequency of 2 to 5 megahertz. Here it's an higher frequency. Here it's a lower frequency. We know that frequency is inversely proportional to penetration. Higher the frequency, it travels lesser the depth. So the linear frequency can travel up to 6 centimeters, so that we can examine only the superficial structures. That's thyroid gland. Whereas in convex probe, curvilinear probe, it is lower frequency, it travels up to a depth of 30 centimeters, so we can examine the abdominal structures, liver, spleen, etc. Okay, this is the concept of frequency and penetration. Then we have another concept of frequency versus resolution. We know that, let us consider, here we have higher frequency, it's reflected back by a superficial structure with the same echo, the echo which is produced as same frequency. Whereas larger frequency, it's reflected by a substance, will have larger echo. The more the echo we are getting, the more brighter the image. More brighter the image, or otherwise known as more resolution will be there. That is better resolution. So the lesser the echo which we are getting back, the lesser will be the brightness or lesser resolution. Therefore, frequency is directly proportional to the resolution. Higher the frequency, higher the resolution. So, as we summarize, linear probe as an approximately, we are using a frequency of around 5 to 10 megahertz. Higher frequency probe, therefore lesser penetration, only approximately 5 centimeters it can penetrate with better resolution. So we are examining the thyroid gland, superficial structures. Whereas curvilinear probe we use 3.5 to 5 megahertz. Here better penetration will be there, so we can examine approximately 30 centimeters depth, thereby, but we have to compromise the resolution. Lesser resolution will be there, so we are using it for abdominal imaging. Whereas phased array probe also has a lower frequency, 1 to 5 megahertz. It's used in cardiac imaging. Thank you for your patient listening.